All right, let's end the week with a very cool application of probability called the probabilistic method. What is the probabilistic method? It is a rad technique for non-constructive existence proofs. So somehow non-constructive existence proofs seem to be a very rich area for cool proof ideas. So here is yet another example. So how it works is calculate the probability that a randomly chosen object satisfies a certain property and observe the very simple observation that if the probability is greater than 0, an example of such an object with such a property must exist. And this is closely related to counting proofs because the probability of something, as we've seen many times, essentially comes down to counting the number of ways it can happen. But this is a very cool interpretation. And also, the techniques of probability sometimes give you techniques that are not super obvious how to interpret in terms of counting. It can be done, I think, for this proof, but it's very clear to write it in terms of probability. That's what we'll do. So the example that we're going to do is bounding Ramsey numbers. Well, but first we need the little lemma. Okay, quick lemma. We are going to get a lower bound on some Ramsey numbers. So we need to get a bound on binomial coefficients that we will use in the course of the proof. So this is just some technical thing, and it is going to play some technical role. So we don't need to worry about it too much. But here's the statement. N choose k is at most n to the k divided by 2 to the k minus 1. And it's quite a simple thing. Let's give a little proof. So n choose k is equal to n factorial, if we remember, divided by k factorial n minus k factorial. And if we cancel this factorial with the rest of the terms in this factorial, what we get is that this is equal to n times n minus 1, n minus 2, etc., down to n minus k plus 1, divided by this thing is what's left on the bottom. That's k times k minus 1 down to times 2 times 1. And so this bound that we're making in this lemma is extremely simple. It's just saying that here we have k terms that are less than or equal to n, and here I'm going to ignore the 1 because we know that the 1 doesn't change the value. If we ignore the 1, we have k minus 1 terms that are greater than or equal to 2. So we can get an upper bound by replacing all these terms with n's and all these terms with 2's, and we get n to the k divided by 2 to the k minus 1. All there is to it. I guess just to note that on the top, these terms are at most n, so we're making them bigger, which makes the result bigger. And on the bottom, they're at least 2, so we're making them smaller, which again makes the result bigger, since you're in the denominator. So there's a little technical lemma that we're going to need. And now let's talk about Ramsey numbers. So recall Rk comma k, this Ramsey number, is the minimum number of people that you need to have in a group. I guess I can write that. Minimum number of people in a group necessary to guarantee either k mutual friends or k mutual strangers. So we proved before that R 3 comma 3 is equal to 6. You will remember this from our pigeonhole principle days. So the claim now that we are going to prove using the probabilistic method is that for k at least 4, RKK is greater than or equal to 2 to the k over 2. So let me rephrase this to make it more clear how we're going to execute the proof. That is, for n less than 2 to the k over 2, there exists, let's say, a configuration of n people with neither k mutual friends nor k mutual strangers. So let's jump into the proof. And it's going to be a little bit more involved probability than we've looked at before, but I hope it will be a good challenge to try and understand, and at least I hope that you will understand what we're doing at each stage, that it will review a lot of the counting and a lot of the probability that we've done so far. So hopefully you can follow each step. Ideally, you will follow the whole idea, but we'll see about that. I'll do my best. So proof. Take n less than 2 to the k over 2. Or I should say, take n people, where n is less than 2 to the k over 2. And we're going to randomly decide whether each pair is friends or strangers. And we're going to compute the probability of finding k mutual friends or k mutual strangers. Let me just write it like this. So, how are we going to do this? So by randomly assigning friends and strangers, let me say what I mean by that for a second. I just mean that we have a bunch of people, and for each pair of people, we're just going to choose them to be friends with probability 1/2 and strangers with probability 1/2. And then we want to compute this probability. So how can we compute this? Let S1, S2, SR be all k-person subsets of our n people. So R is equal to n choose k, because this is the number of k element subsets of a set with n elements. And define E1 through ER, the events defined by, so EI is the event that SI consists entirely of friends or entirely of strangers. In which case SI will be a set of k mutual friends or a set of k mutual strangers. So essentially, we're breaking this event, that there are k mutual friends or k mutual strangers, down into a collection of events based on exactly which set of people is k mutual friends or k mutual strangers. These are all the possibilities. So given k people, so for example, any of these sets S sub I, probability of all friends, what is this? So we are assigning each pair to be friends with probability 1/2. And how many pairs are there? K times k minus 1 over 2. So let me just write that out, because there are k choose 2, which is k times k minus 1 over 2 pairs of people. And same for the probability of all strangers. So the probability of EI, let's think about what this is. It is, given this group of k people, that it consists entirely of friends or entirely of strangers. So those two possibilities are disjoint, so we can just add the probabilities for each of them. And those are the same, so it's just 2 times 1/2 to the k minus 1 over 2. And now, at this point, we have all our setup, and we can kind of just go compute this thing. So it may not be obvious what we're doing at each step, but remember that our goal is to show that this thing is strictly less than 1. So let me explain this goal for a second. Let's take stock of where we're at. We want to show that for this n people we've chosen, there exists a configuration with neither k mutual friends nor k mutual strangers. So that is the same as saying the probability of getting k mutual friends or k mutual strangers is strictly smaller than 1. Now, that's part of this formula. The other part is that I've swapped out the things inside the probability. What are we doing there? We're saying that the probability of getting k mutual friends or k mutual strangers can be broken down into precisely which k group of people are all friends or all strangers. So the SIs are all the k-person subsets in our group, and the EIs are just saying that that is the k-person subset that consists entirely of friends or strangers. So if we take the union of the EIs, this is just saying that there is some set of k people which is entirely friends or entirely strangers. So if we can show that this thing is strictly less than 1, That will complete the proof. Okay, so having taken stock of that, let me maybe write it down a little bit more clearly. Not the whole thing, but let me just say we want this. And I'll note also that this is the event that some subset of k people is all friends or all strangers. So the reason that I'm stopping here to give a little overview and take stock is because from here on out, it's just a big computation. So maybe we'll just blaze through that without dwelling too much on each of the steps. So, or maybe this is the point where I will stop thinking about the big picture and start thinking about reviewing some rules of probability. So you will remember that the probability of a union of events, if they are disjoint, it is equal to the sum of the probabilities. If they are not disjoint, all you can say that it is less than or equal to the sum of the probabilities. So in this case, they are not disjoint, so we don't know that this is equal, but we know that it's less than or equal. And now let's just write out the probability that we wrote here. Oops, not that. 2, 1/2 k minus 1 over 2. And that, so all of our terms are the same in this sum. And we have, yeah, let me write this a little more clearly. I forgot that I did that on purpose, that I could do that. So I is going from 0 to r, right? Because I guess from 1 to r, now that I'm looking back at our thing, that makes sense too. I is going from 1 to r. So we have r terms in our sum. And remember we said that r is n choose k because it's just all the possible k person subsets. So r is n choose k. We have this many terms in our sum. So this sum is equal to just n choose k times that common value. And this is where we will plug in our little quick lemma. Remember, this was saying that this guy, n choose k, is not equal to, but less than or equal to n to the k divided by 2 to the k minus 1. And from here, we remember we assumed at the beginning that n is less than 2 to the k over 2. That's essentially the bound that we're putting on the Ramsey number. So since n is less than 2 to the k over 2, this is strictly less than 2 to the k over 2 to the k over 2 to the k minus 1 times 2 times 1/2 k minus 1 over 2. Cool. All right. And now we have a big old formula with a bunch of 2's and a bunch of k's. And I'm just going to simplify it all in one step. This is just 2. If you expand out all these powers and put them all together, it's just 2 to the 2 minus k over 2. And this is less than or equal to 1 if n, if k, as we have assumed, is greater than or equal to 4. So if k is 4, this power is 2 minus 4 over 2, which is 0. 2 to the 0 is 1. If k is bigger than 4, then the negative k is going to make it smaller and smaller. So to summarize, if you follow this chain of inequalities and equalities, this thing is strictly less than this thing, which is exactly what we wanted to show, and that completes the proof. Let me just say, as desired. So, let me zoom back out a little bit. You can see that this proof is a little bit more complicated than most of the stuff we've seen so far. Quite a long one, but it is a very nice illustration of a very cool method. So let's just recall what we did. We wanted to show that there existed a configuration of n people with neither k-mutual friends nor k-mutual strangers. And the way we did that was we chose the configuration at random, and we showed that the probability of finding such a configuration was greater than 0. And you can conclude then that one exists. How cool. And what's even cooler, I think I mentioned this in a previous lecture and mistook it for an exercise, but it has appeared instead in this form. But in fact, I believe this was proven in oh geez, did I write this correctly? 1947, I think this was proven. So it's quite, by some standards, quite old. But to this day, it remains the best lower bound, best known lower bound on this number, in the sense that we've shown that RKK is greater than or equal to 2 to the k over 2, but let's rewrite this using our exponent rules. This is just square root of 2 to the power k. And what I mean by the best known lower bound is that no one has been able to replace this square root of 2 with a bigger number. So this is an exponential lower bound, and if you increase the exponent factor, or the factor of, the factor of growth, then that will give you a better lower bound. But the point is that no one has ever done that, at least for this, so far. This is still the best known lower bound. And yet you can prove it with these fairly elementary methods. So it is simultaneously, in my opinion, an extremely cool example of the probabilistic method, and also an extremely cool example of how mysterious these Ramsey numbers are. That this very cunning but quite simple proof is still the best we have done since 1947.